Okay, so last time we were talking about chapter 8 and really how to calculate empirical formulas. And really there's a few steps to do when you calculate an empirical formula. The first thing you want to do is convert to grams. And again, that's a case where you're perhaps given everything in percent composition by mass. You could assume that there's 100 grams and convert those guys into grams. The next thing that you want to do is take those grams and convert them to moles using the molar mass to do so. At this point, you will have basically moles of all your elements. You then want to divide by the smallest number of moles. And at this point, if you do hit all whole numbers, then that would be your empirical formula. I think like the example we finished up on, and in some cases, you don't necessarily always will hit whole numbers at this point. You may have to sort of figure out a factor to multiply. I think maybe in the last one we did, we had something like 1.33 as one of the values. So at that point, that is, again, too far to round. Really, it does need to be pretty much on the whole number to be sort of acceptable to round. In this case, we would multiply it by 3, which does give us something like 3.99, which was appropriately about 4. So if you do not hit sort of a whole number on all of them, because the formula obviously does need to have whole numbers, you do need to figure out a factor to multiply, not just the one that's not a whole number by, but the entire sort of formula by that factor to get to your empirical formula. Again, if it's fairly close to the whole number, like, 99, 98, a little bit over, like, 0.03 or something like that, that's close enough to round. But, 0.33, like a 0.25, a 0.5, those are sort of too far to round to the nearest number. Any questions on that there? All right, then let us try another one here. What is the empirical formula of a compound that's 1.078 grams and contains 0.54 grams of sulfur and 0.538 grams of oxygen? Sulfur on the periodic table is 3207. Oxygen is 16. All right, take a minute or two, see what you come up with. Okay, let's take a look and see. So in this particular case, a little bit different than one we did last time, which had the percent composition. This is a sample that contains sulfur and oxygen only, has a total mass of 1.078 grams. It is 0.54 grams of sulfur and 0.538 grams there of oxygen. So in this particular case, we really don't need this number other than the fact that we probably should take both of these numbers, add them together just to make sure it does add up to that. Again, if it did not add up to that 1.078 number, we would be missing something in this case. But since we do take 0.54 and add it to 0.538, that essentially is 1.078 grams. That means we got everything that should be in that compound at that point. And really, we could pick up with it's already in grams, so we don't need to get the percent composition just to get it back to the grams. So we could start with our grams here, and we're going to convert them into moles. So 0.54 grams of sulfur, we will divide it by 3207 there for sulfur. We'll take our 0.538 grams of oxygen, divided by 16 grams per mole. That is going to get us for our sulfur 540 by 3207. We'll call it 0.0168 moles of sulfur. And for our oxygen, 0.538 divided by 16 gets us a 0.0336 moles of oxygen. At this point, we have converted it into moles, and we now want to divide by the smallest number of moles, which in this case is sulfur. So we're basically going to divide everybody there by the moles of sulfur. That obviously gives us a 1 for the sulfur, and dividing this guy here should give us approximately a 2. And that means we did hit, in this case, all whole numbers. So we are good to go as that being our empirical formula of SO2. little sulfur dioxide. Yes. Any questions on any of those steps here? So again, this is another way that sometimes these problems will be given to you. I mean, maybe not the percent composition, but you'll be given the grams of each of them just straight out. And then you could just roll from there. Questions on that? Okay. All right, one more here. What is the empirical formula here? If we got 49.3% carbon, 6.9% hydrogen, and 43.8% oxygen. Carbon 12.01, oxygen 16, and hydrogen 1.008. Let's take a look. So again here, just quickly taking a peek at the percentages, they do add up to about 100%. So that is good. That also means, like we talked about before, we could just assume that we have 100 grams of everything. That basically will just turn our percentages into grams, keeping the numbers the same. That means that we technically would have 49.3 grams of carbon, which we would then want to convert into moles by dividing by 1201. We would then have 6.9 grams of hydrogen, which we would divide by 1.008. And we would have 43.8 grams of oxygen, which we would divide by the molar mass of oxygen, which is 16. That again will turn us all into moles here. That gets us 49.3 divided by a 1201. We'll call it 4.105 moles of carbon. 6.9 divided by 1.008 gets us a 6.845 moles of hydrogen, and 43.8 divided by 16 hits us with a 2.738 moles of oxygen. In this case, just like before, we're going to divide by the smallest number of moles, which looks like in this case, it is going to be the oxygen. So we're going to divide this guy by 2.738, 2.738, and 2.738. That gives us a 1 for the oxygen. For our carbon, gets us a about 1.5, and for our hydrogen, gets us about a 2.5. At this point, if we were to write our empirical formula, we would have C 1.5, H 2.5, and oxygen. As we talked about, it does have to be whole numbers, so we do need to clear these guys. In this particular case, we could actually clear both of them by multiplying by 2, right? If we multiply by 2, that will turn our carbon into a 3 and our hydrogen, I think, into a 5. So remember that the factor in this case, we want to multiply by 2, but everybody that is there, that would get us a C3H5O2 as our correct empirical formula. Any questions on that one there? Question? No? No, honestly, you don't want to round too much here with the moles, especially in this case, because you're going to come back and divide by the moles. So if you do a lot of rounding, you may find yourself not very close to like whole numbers in certain cases. So in this situation, since this is really not necessarily our answers to the problem, these numbers here, I typically take it to a good number of digits. That way, you know, you could then make the decision to round if it's close to a whole number. Again, if you go really strict on these numbers and then you start to divide, you may find yourself not near any whole number and not be able to really find a correct factor to kind of clear it if it's not. So my recommendation is, since these are technically not really the answers, to take it to a good number of digits. And then at the end, when you divide over here, you know, this is where, you know, you're really interested in those last numbers and stuff like that. Yeah. Other questions? Okay. All right. So that obviously is how to calculate empirical formulas. There is also, we could also calculate the molecular formula as well. So we have empirical formula, as we talked about, which is the simple representation of what is present. We can also calculate pretty much the molecular formula as well. You basically need three things. You need the empirical formula, which either it's given to you in the problem or you need to calculate it like we've been doing. You need the molar mass of the empirical formula, which also obviously either it's given to you in the problem, the empirical formula, you calculate the molar mass, or you calculate the empirical formula, then calculate the molar mass. The last thing is you need the approximate molar mass of the compound, which is number 1 here. That is usually given to you in the problem. So somewhere in the problem, they will say, hey, this guy has a molar mass of 100 grams. They may even say this guy has a molar mass somewhere between like 90 and 100. They may actually give you a range or something like that. But somewhere in the problem, they'll give you some information about what the molar mass is of the actual compound of the molecular formula. And what you do with that is you basically take the molar mass that they give you, you take the molar mass of your empirical formula, and you divide them. And when you divide them, it will give you a number. And this number is basically the factor by which you multiply the empirical formula by to get to the molecular formula. So let's just say we had our like C2H4 as our empirical formula. Let's say we divided and we got like a 4. Our molecular formula would be C8H16. We would multiply basically this guy by 4, and that's what we'll do. Now, the one place where it's really okay to sort of round, even if it's really not necessary right on a whole number, is when you're doing this part here. And that's because sometimes you're given like an apparent molar mass, an approximate molar mass may not be perfectly right number. You might have a range like we just talked about where, you know, you might, depending on which number you pick it within that range, you may not get exactly a whole number. So in this case, when you're figuring out the molecular formula and doing this little division here, it is okay to round to the nearest whole number, and that will get you to what you need. Again, when I'm talking about, you know, if they give you a range of like 80 to 90 grams per mole, you know, you technically could pick 80 for the molar mass. You could technically do the calculation with 90. You could go right in the middle if you like, or any number in between. And depending on which number you get, you may get a slightly different factor when you kind of divide it out. So in this case, you can round to that nearest number and it would be okay. So let's take a look at one here. So the empirical formula for acetic acid is CH2O. What is the molecular formula if the approximate molar mass is 60? So in this particular case, we don't actually have to calculate the empirical formula because they were nice enough to give it to us. So again, if they don't give it to you, you do need to calculate it like we did before. So that's one of the things that we need. The second thing that we need is the molar mass of the empirical formula. So that would be 12.01 plus 2 times 1.008 plus a 16. And that would get us looks like about a 30.03 grams per mole. So now we have the empirical formula. We now have the molar mass of the empirical formula. And this is the approximate molar mass of the compound, which is really the third thing that you need. So we're going to take the molar mass of the compound that they gave us. We're going to divide it by the molar mass of our empirical formula. So molar mass given, molar mass of the empirical formula. And that gives us basically a factor of 2 in this case when we divide, obviously 60 divided by 30.03 gets us basically like a 1.998, which is basically a 2 in this case. That 2 we're going to multiply our empirical formula by, which would give us C2H4O2 as the molecular formula in this particular case. Another way, sometimes people write it, but not a lot these days, but sometimes you will see people just sort of put the empirical formula in parentheses and put the little factor of 2 on the bottom. Most people will kind of distribute the 2 and write it like this for the molecular formula, but you still sometimes see in books and stuff like that, people kind of do it like that. I would recommend probably distributing it. That's usually how most people will do it in terms of the molecular formula. So again, those are really the three things that you need to calculate the molecular formula. You need the empirical formula. Either you got calculators given to you, like it was in this problem, molar mass in the empirical formula, and obviously the given property, which is the molar mass of the compound. Any questions on that step there? All right, so why don't you try one here, I think. All right, a compound contains nitrogen and oxygen. It has a molar mass between 90 and 95 grams per mole. Determine the molecular formula. Nitrogen is 1401. And oxygen is still 16, I think. Okay, let's take a look. So in this particular case, we are looking for the molecular formula. We do need the empirical formula. They did not give it to us. So that's really the first thing that we do want to calculate is the empirical formula like we did before. So we'll take the 1.52 grams of nitrogen. We will divide it by 1401 to convert it into moles. We will take the 3.47 grams of oxygen, divide it by 16 to convert it into moles. And that gets us 1.52, 1401, gets us 0.1085 moles of nitrogen. 3.47 divided by 16, 0.2169 moles of oxygen. In this case, just like before, we're going to divide by the smallest, which looks like it is the nitrogen in this case. So we're going to divide them both by the nitrogen's value. That gives us 1 for nitrogen, and for our oxygen gets us basically like a 1.998, which is about 2. So that again is close enough to round in this case. That gives us an empirical formula of NO2. The second thing that we need now that we have the empirical formula is we need the molar mass of it. So that's going to be 1401 for the 1 nitrogen plus 2 times 16 for our 2 oxygens, gives us 4601 grams per mole, which would be the molar mass of our empirical formula. In this particular problem, as we talked about earlier, we have really a range for the molar mass that was given to us. So you could choose anywhere along that range you want. So if we did the 95, which is the high end, divided by our 4601, that gets us about 2.06. If we did the low end, which was 90 divided by 4601, gets you about 1.96, which is approximately 2 as well. And if you felt like, hey, why don't we just go right dead in the middle there at 92.5, right? You obviously don't need to do all 3 of the calculations. You can pick any one of them. This gives you like a 2.01. So no matter where you kind of choose along that range, we are basically hitting 2 as our factor there to multiply our empirical formula by. And if we do that, that should give us an N2O4 as our molecular formula. Any questions on that there? I guess it also asks for the molar mass of the molecular formula. 9202 grams per mole would be the actual molar mass of this molecular formula. And as you can see, that's basically kind of close to this number here in the middle of that range. Question on how to calculate molecular formulas here. All right.